So welcome to the video. Today we're going to take a look at how to do an independent t-test on version 31 of SPSS. So we're typically going to use this test when we have an independent variable comprised of two levels, so that's a categorical variable, and when we have a continuous dependent variable. So for this example, we are going to imagine that we have some people who have been allocated to a high protein diet, and that's represented by the number 1. So anyone who has a number 1 is in the high protein diet group. And we have people represented by the number 2 here who had a standard diet. And we're interested in whether there's a difference between those groups in terms of how much muscle they gained after a certain period of time. And so that's the information that we have in this column here. So this person here gained 2 kilograms of muscle. So let's take a look at how to put these data into SPSS. So we can go down to variable view to start with, and then we can give a name to the independent variable in this name column. So let's call this something like diet, and then we can give a name to the dependent variable. So let's call this something like muscle underscore gain. So I'm just using an underscore there because I can't use a space. And then we can use this values column to specify what the levels of the independent variable were. So if we click on this little box here, that'll open this window. And then if we click this plus button, we can say that 1 equals high protein diet. If we click the plus button again, we can say that 2 equals a standard diet. Then we can go to OK when this looks like this, and we can use this measures column to specify that diet is a nominal variable, which is sometimes referred to as a categorical variable, and we can use the measures column to indicate that muscle gain was a scale variable, which is sometimes referred to as a continuous variable. So once we've done that, we can go to data view, and we can see that the names of those two variables appear at the top of these two columns. So we're ready to paste the data in. So we can go to this spreadsheet. I'll select the top left cell, I'll go down to the bottom, and whilst holding shift I'll click the bottom right cell. Then I'll go to Command or Control C to copy those data, and then I'll go back to SPSS and I'll press Command or Control V while I have the top left cell selected to paste those data in. Sometimes that doesn't work, so you have to go to Edit and then down to Paste, and that should paste those data in. We can see that we have high protein diet and standard diet in this column, rather than the numbers we had in the Excel spreadsheet, and that's because of course we allocated those descriptions to the numbers 1 and 2, and it's also because in the view menu we have value label selected. If we unselect that, we just see the numbers instead. I'm going to keep it selected, but let's take a look now at the assumptions of this test. So it has a couple. One is that there is a normal distribution within each of the groups, and the other is that there is homogeneity or variance. And as I've mentioned in this notes here, if you find that one of these assumptions isn't met, you could consider doing a Mann-Whitney U-test instead, which is the non-parametric equivalent of the independent t-test. So we can check this homogeneity or variance assumption as we run the test, but we should check this normality assumption before running the test. So to do this, we can go up to Analyze, and then down to Descriptive Statistics, then across to Explore, and then we can transfer our independent variable to the factor list and our dependent variable to the dependent list. We can then go to Plots, and we can tick Histogram, and we can untick Stem and Leaf, and we can tick Normality Plots for Tests. Then we'll go to Continue and then to OK. And then if we scroll down slightly to this tests of normality table, we can see that we actually have 2 normality tests. So we have the Kolmogorov-Smirnov test on the left, and we have the Shapiro-Wilk test on the right. And we typically use the Shapiro-Wilk test when we have fewer than 50 participants or data points per condition. And we typically use this test on the left when we have more than 50 data points per condition. So we can see here that we have 30 people in each of our conditions. So we're going to focus on the Shapiro-Wilk parts of the table, and specifically we're going to look at this SIG column. And what we want to see is that these values here are below 0.05, as that would suggest that the data are normally distributed in each condition. However, we can see here that both of these values are below 0.05, indicating or suggesting that the data are not normally distributed. So actually, if I saw this, normally what I would do would be to switch to a man-Whitney U-test, because that doesn't make an assumption about the data being normally distributed. However, as this is just an example, we're going to continue with the independent t-test anyway. You can also look at the histograms to try to determine whether your data are normally distributed. What you would want to see is that you have a symmetrical bell-shaped distribution. So these histograms don't actually look a million miles away from that. You can tell that there's a bit more going on to the left, so they're a little bit asymmetrical. But I would tend to favor determining whether your data are normally distributed by looking at these normality tests, because they give you a more objective answer about whether or not your data are normally distributed. So let's continue with the test. Let's go up to Analyze and then down to Compare Means and Proportions, and then across to Independent Samples t-test. And then we can transfer our dependent variable to the test variables box and our independent variable to the grouping variable box. We need to tick homogeneity of variance tests. And if we click on our independent variable here and then on define groups, we can see that we have 1 and 2 here as the default. And this corresponds to actually how we set up the file. So we set that 1 equals the high protein diet condition and 2 equals the standard diet condition. If we had instead used, for example, 0 and 1 to represent those two conditions, we could replace 1 with 0 and 2 with 1. However, as this is how we set up the file, we can just leave this as it is. So we can go to continue and then to OK to run the test. And the first thing I'm going to look at is this homogeneity of variance test table, and at the sig column here, and we can see that we have a value of 0.679. So as this is above 0.05, it indicates that the assumption of homogeneity of variance has been met, which essentially means that the data are spread out to a similar extent in the two conditions. And what you see here determines which row you look at in this table here. So if you have a value above 0.05, you're going to look at the top row here. And if you have a value below 0.05, it would indicate a violation of this assumption, and you would instead look at this row here. So I'm going to look at this equal variances assumed row, and I'm going to look at this significance part of the table, and we actually have two options here. So we can either look at this one-sided p column, or we can look at this two-sided p column, and which you look at depends on the type of hypothesis you had. So if you had a one-sided directional hypothesis, you would focus on this column. And if you had a two-sided or non-directional hypothesis, you would look at this column on the right. So a one-sided hypothesis in this case would be something like, it was hypothesized that muscle gain would be significantly greater in the high protein diet condition compared to the standard diet condition. Conversely, a non-directional or two-sided hypothesis would be something like, it was hypothesized that there would be a significant difference between the conditions with respect to muscle gain. So the two-sided hypothesis is less specific than the one-sided hypothesis. So let's imagine we had a one-sided hypothesis. So I'm going to look here and we can see that we have a p-value of less than 0.001. And as this is less than 0.05, it indicates that there's a significant difference in muscle gain between the two conditions. And we can find out more about that if we look at this group statistics table and at this mean column. We can see that in the high protein diet, we had a mean muscle gain of 4.7, whereas among those who had the standard diet, we had a mean muscle gain of 3.63. So the muscle gain was greater in the high protein diet condition compared to the standard diet condition. So that's essentially how we interpret the results of the test, but let's now take a look at how we can write up those results. So I've started off just by saying why we did the test. So I've said that an independent samples t-test was conducted to compare muscle mass gain in the high protein diet and standard diet conditions, and then I've referred to those Shapiro-Wilk tests that we conducted. So I said that Shapiro-Wilk tests indicated that the data were not normally distributed in the high protein diet condition or in the standard diet condition. As I mentioned before, if I saw that, I would actually switch to doing a man-Whitney U test instead, but I'm just going to ignore the fact that the data were not normally distributed for the sake of this example. So we have some stats here, so we can take a look at where those come from. So for the high protein diet condition, we have a W value of 0.86. So let's take a look at where that is coming from. If we go to this tests of normality table, And if we look at this high protein diet row, we can see in the statistic column that we have a value of 0.86. So that's that double U value. We also have a degrees of freedom value of 30 and a sig value of 0.001. And that's what we have here. So here's the degrees of freedom in brackets, and here's the p-value. And then we've just reported the same 3 statistics for the standard diet condition. So those 3 statistics are coming from these 3 columns here. Next, we've reported the results of Levene's test. So we've said that Levene's test indicated that the assumption of homogeneity of variance was met. And then we have an F value of 0.17 and a P value of 0.679. So if we scroll down in this output, we can see here that we have the F value of 0.17. So we're looking at this homogeneity of variance test table. And we have the sig value or P value of 0.679. And then next we get to reporting the results of the t-test itself. So I've said that muscle mass gain was significantly higher in the high protein diet condition than the standard diet condition. And then we have these means and standard deviations for both conditions. So for the high protein diet condition, we have a mean of 4.7 and a standard deviation of 0.92. So if we look here in the group statistics table and the high protein diets row, we have a mean of 4.70 and a standard deviation of 0.92 if we just round that value there to 2 decimal places. And then we've reported the mean and standard deviation for the standard diet condition, which is just coming from the same table but in the row below. And then we have the results of the t-test. So we have t equals 4.39, and that's coming from this independent samples test table and this equal variances assumed row, where in the t column we have a value of 4.39 rounded to 2 decimal places. We have a degrees of freedom value of 58, and we have a p-value of less than 0.001. So those are all the values that we have here. So there's the degrees of freedom value, there's the t value, and there's the p or sig value. And lastly, we've said that the effect size was large, and we've reported a Cohen's d value of 1.14, and that value is coming from this independent samples effect sizes table, where we have a Cohen's d row and a point estimate column, and we're taking this value here and rounding it to 2 decimal places to get 1.14, and we've described that as large based on these criteria here. So Cohen's d values between 0 and 0.2 are typically considered to represent very small effects. Those between 0.2 and 0.5 represent small effects. Those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. And these same criteria apply if we have minus symbols as well. So here we have a value of 1.14, and as this is larger than 0.8, we've described that as a large effect. So that's about it for the independent t-test on version 31 of SPSS. I hope that was helpful. If you have any questions, just let me know in the comments, and I will try to get back to you. Thank you very much for watching, and I'll see you next time.